Good afternoon, everyone. Today we have the 13th.
YouTube live is okay?
1 second, sir. Let's say check.
Yeah, it is now streaming, sir.
Yeah.
Go ahead.
So, ma'am, you can. Yeah.
Okay. Good evening, everyone. Today we have 13th lecture in the weekly online lecture series on radar meteorology, organized by South Asian Meteorological Association and ACARR CUSAT. Today we are lucky to have Dr. Soma Roy, scientist from India Meteorological Department. Before starting the lecture series, I invite Professor Someshwar Das sir for the welcome address.
Thank you, Dr. Srikala. ABM Professor Tyagi Saab, the President of Soma. Today's distinguished speaker, Dr. Soma Roy, our organizing committee members, Dr. Swagat Paira, Dr. Srikala, Rakesh, Dr. Kyal Wing from Myanmar, and Mr. Salam from Bangladesh. So, very good afternoon. We welcome you on behalf of the South Asian Meteorological Association, as well as the ACARR, the Advanced Center for Atmospheric Research at Cochin University of Science and Technology. As said already, today is the 13th lecture being delivered by Dr. Soma Roy. In fact, I would like to thank her very much because despite her busy schedule, as she said just now, that she wanted to start it earlier because of some other engagement programs at IMD. But on my request, she agreed to start the lecture at 3 o'clock, considering the participants who are from so many countries and they live in different time zones. So if I change the time, then all the participants will be disturbed. So anyway, thanks a lot to the speaker, Dr. Soma Roy, for agreeing to start at 3 o'clock. As you know, she is the first speaker of our lecture series on radar meteorology. So I would like to say briefly about our lecture series. This is a continuation of our efforts on capacity building of the people of South Asia and the member countries of the non-aligned movement. Has already been said many times that this is our fourth lecture series. The first one was organized on atmospheric physics jointly with the SRM Institute of Science and Technology. The second one was training on WRF modeling system, which was organized jointly with the CDAC, that is the Center for Development of Advanced Computing. The third one was organized jointly with the BIT MESRA on satellite meteorology. That was organized for 20 weeks. And this is the fourth lecture series on radar meteorology, which will also last for about 20 weeks or almost 5 months. We have got a very distinguished panel of senior scientists and professors from reputed institutions of this region who are experts in the field who are delivering lectures. The syllabus of the lecture series has been designed based on the feedback and requirements of the member countries of Soma. This lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of radar meteorology. As has been said many times, almost 1,200 people from about 48 countries have registered for this course. As said many times earlier, at the end of the lecture series, we shall conduct a test, online test. We have already conducted one midterm test after 10 lectures were over, and the final test will be conducted after all the lectures will be over. We also count the attendance, and based upon the attendance, we shall give a special certificates to those who will attend more than 75% of the lectures, and those who will score in the final test more than 85% or more than 80%, they will get different grades like outstanding, excellent, very good, etc. So, as said earlier, this lecture series is being live streamed on the YouTube. all the past lecture series are available also on the YouTube, and I see time to time that we are getting good hits. The lecture series is very popular. Already the first one was viewed by more than, I think, 1.5 thousand people. And this number obviously increases day by day. And all the participants know you have to write down your questions in the question and answer box, and it will be taken up by our moderator at the end of the talk, and it will be answered by the speaker. So please write down your questions on the question and answer box, chat box. So invite the lecturer for today, and on to you, Dr. Srikala.
Thank you very much, sir. Now I welcome AVM Professor Ajit Tyagi, sir, for presidential address.
Good afternoon, and thank you, Dr. Srikala.
Thank you, sir.
Our distinguished colleagues from Myanmar, Dr. Kya Lwin Wu, and from Bangladesh, Shah Alam, members of the organizing committee, so efficiently conducting this series of lecture. Thanks to ACARR team. Professor Someshwar Das has given you the entire background of our lecture series and how we are able to reach to large number of young students and researchers in 48 countries, and they are being followed by question answers and the midterm tests and the following by the final test. So this is very well organized and comprehensive program, and we are getting good feedback, but this wouldn't have been possible without the support of our eminent speakers. And I am happy today we have I think seasoned forecaster Dr. Soma Sandroy. Actually, the use of any technology and essentially for the services is to use this application in the real forecasting. And for radar, the nowcasting is the most powerful, usage. And I'm happy that Dr. Soma Sandroy, she have extensive first-hand experience of using satellite radar data in nowcasting. Various software tools are there which use these, but the real efficacy of this is when you practically apply this and have it's verified its efficacy in using the nowcasting. So today we'll have her viewpoint that how best we can use the radar. You see, in next 5 to 10 years, the number of radars in the country are going to be many-fold. I had been interacting with many agencies which are now thinking to put radars complementing the IMED radar network. So it's good for not only for IMED but all other operational agencies and the young researchers to have in-depth knowledge about the radar products and its application. So once again, thank you, Dr. Soma Sandroy, for having spared your time. I know during cyclone and monsoon period, a forecaster in IMED is always in great demand and have to be update everyone. So thank you, and wish this lecture great success. Thank you.
Thank you very much, sir. Before starting the lecture, I invite Dr. Swagata Paira to give a brief introduction about Dr. Soma Sandroy.
Thank you, Dr. Srikala. I could say that Dr. Soma ma'am is so polite that we have asked the latest CV, but she told, okay, whatever the things we feel when we can introduce. So I could say Dr. Soma Sandroy is a senior meteorologist at the National Forecasting Center of India Meteorological Department at Delhi. As an operational weather forecaster, she heads the Nowcast Services Unit for severe weather of the division. She has working experience in weather radars, weather satellites, and Nowcast models. Her specific field of interest is tropical thunderstorm and their improved nowcasting in an operational context. Ma'am, floor is yours. You can share the slide and carry on.
Thank you very much. I'm in the presence of some of the biggest people in this field. Dr. Tyagi sir permitted me to be in nowcasting, and the first few years he has guided us. So I'm grateful to Tyagi sir, especially, and of course Someshwar Das sir and others I'm seeing in the group. If I'm not individually thanking you, please understand I'm grateful to all of you for permitting me to share the limited knowledge that I have in this regard. Can you see my screen?
Yes, ma'am.
Can I put it in presentation mode? Yes. Is it now visible?
Perfect.
Yes, ma'am. Yes, ma'am.
So this is about how we use radars operationally in India Meteorological Department. So if we see our history of Doppler radars, I will not, I'll just say that from 1954, we had the first radar post the Second World War. There were a lot of additional radars available. We managed to hook on to one or two of them, and then finally our first radar came up in Kolkata, and thereafter we've had generations of weather radars. The first Doppler weather radar, you can see it had come in Kolkata in 2003. Immediately thereafter, the next radar came up in Chennai. So these two stations were considered important in the sense because these were stations where on the east coast we had a lot of tropical cyclones. These were S-band Doppler radars, and the focus was primarily on tropical cyclones initially. Thereafter, the need was felt that Doppler radar network should be expanded, and Tyagi sir is here. He will attest to the fact that first the East Coast radars came up, then gradually the radars were populated in the interior, and now we have 39 Doppler weather radars throughout the country. As Sumeshwar Das sir said that Doppler radars are the future. We really there are some radar holes still remaining, but the idea is now to go for urban radars. So the increase in radar usage is only likely to increase further in the coming years. When we talk of Doppler radar usage, we have an entire network. I have not mentioned the network, the difference, but we have Doppler radars in the S-band, C-band, and X-band. I think you've already been told about this. So I will not touch more about this. We have dual polarized radars. We have radars which are portable radars. So a lot of variety of radars are there with India Meteorological Department. Coming directly to the subject of our concern, if we start at time t is equal to 0, that means if we start from right now, if we have to give a forecast, the easiest thing is to look out of the window and say, oh, it is raining, so it will continue to rain. We all know from experience that the first few minutes, generally we are right. So we can say it's 100% accuracy. Thereafter, the persistence-based forecasts, depending on the season, decays very quickly. Better technique is the extrapolation-based forecast. So there, the starting from observations, you extrapolate. If the rain is decreasing, you say gradually decreasing trend, and it is likely to end in the next 5 minutes, 10 minutes. So that, or 1 hour or 5 hours. So that gives you are basically extrapolating the present situation into the future. The third situation is that we focus on numerical weather prediction models, which solve primitive equations, give you a forecast. Now, if you see the accuracy, applicability on the y-axis and the lead time on the x-axis, generally you will find that persistence-based forecasts decay most quickly, accuracy. Extrapolation decays more slowly. And NWB models, from the time of if you say a zero UTC model, the first couple of hours, depending on the model and its resolution, the first few cycles of the model output will not be very usable because models face a spin-up problem. So because of that, most countries are now going in for nowcasting based. So there has to be a transition from observations to numerical weather models. And again, if you go to weeks and months and season, like if you're planning to visit Goa in the month of December, you will say that, oh, it will be clear skies and very sunny skies. So more or less, most of the times you will be right. But again, you need to, if you want to go increase your accuracy, you have to depend upon the actual weather forecast, which is based on your numerical models. So why I'm saying this is because nowcasting occupies a very small part of this entire forecasting framework. It starts from observations, that is what is happening right now. It goes on using extrapolation, persistence, it goes on pushing the forecast accuracy to the next few hours. And thereafter, it merges with numerical weather prediction models to give a seamless transition from the observations to the prediction. So this is the basic purpose of nowcasting. That means anytime you are giving a nowcast, we will focus observations, their extrapolation, and then NWP models. That is how we follow at every cycle. And that is through a standard operating procedure in IMD. We are discussing mainly radar, but these are little background material I thought we should have in mind before we discuss the position of radar in this whole thing. Clearly then that radars are observations, but they have a utility in numerical weather prediction models as well as in extrapolation and persistence. So if you see radars, basically radar output comes again in the scale of 1 to few hours, depending upon the way one is using the radar data. Now, when we start with our forecasting is a very, especially for thunderstorms, forecasting is a very 0-1 task. You're either right or you're wrong. I mean, you give a forecast based on you have to say within 3 hours, 4 hours, 6 hours, whether there will be a thunderstorm or not, there will be the thunderstorm. Now, unlike rain forecast, where if you give 6 centimeter and 4 centimeter can come, you can say your forecast is more or less right. In thunderstorm, it is a 0-1 case. Either you hear thunder or you don't hear thunder. So that makes the task of a forecaster for predicting thunderstorms so much more difficult. Just to give you this idea that you're starting at a cumulus stage, you have to see all factors. The observation may be at the cumulus stage. You have to see all factors to predict that it will reach cumulonimbus stage and it will give a thunder. That is what is your target. So this kind of a difficulty is the task of an operational forecaster throughout India. We are especially vulnerable because Indian weather occurs in a very conditionally unstable atmosphere. Again, I request you that anybody who has a question can please interrupt me, because this is a classroom kind of thing. So this is not I welcome questions if you want to know more. So cumulus cloud, when we are talking of its development into cumulonimbus, it is not just radars that will come into use, but every other equipment where radars form the last stage in deciding the forecast. This is one of the biggest achievements, I can say, for the initial phase of our Doppler radar usage. Now there have been much bigger achievements, and the first thing was we managed to make the data uniform and follow a uniform scan strategy. This is very important when you're trying to ingest radar data into numerical models or use them for any purpose which requires automation. So there, if you see our current scan strategy, this is based on the VCP21 of the WSR88D network of USA. But the benefit of this radar is that it has closer spaced beam angles, which at lower elevations, which makes the lower part of the cloud more detailed sampling can happen, whereas the upper part of the cloud is less well sampled. This scan strategy was not just based on was created not just based on the on sampling, but also the pressure that radar network at that time could take, because the radar has to turn at a certain speed to be able to complete all these 10 elevation scans, come back to 0, again start the next scan. So all those things considered, this was the scan strategy decided. Now, if you consider this from an operational point of view, this scan strategy has certain problems, which is what we need to keep in mind when we use the radar data. First of all, close to the radar, you will note that the highest beam, 21 degrees, there is no beam beyond that. So if a cell is directly over the radar, you can say there is a cone of silence around the center of the radar when the radar is not able to detect any echo. The other thing is, if you suppose you see a cell, let me try to make it a pen. If you see a cell that is located, suppose here, versus the same cell when it comes closer, can you see these arrows coming? These clouds? Can you see, or am I just...
Yeah, we can see, ma'am. We can see.
So if you see one thing, the main, when you see a cell which is coming closer, the lowest elevations in the initial, when it is further away, is not sampled by the radar. That is a problem, and there is ground clutter which creates problems in the lowest elevation. So this beam bending is due to earth bending that you must have already heard about. But the problem then is that we tend to not sample the lowest part of the thunderstorm cell. What happens is, during the decaying stage of a thunderstorm, we are not able to see what exactly is the actual, we cannot calculate, suppose, the surface rainfall rate, because we are sampling much higher up. We are not able to see what is the lowest level phenomena that are happening, because we are not sampling it. As it comes closer, so you can say around 100 kilometer height, 100 kilometer distance, 100 to 120 kilometer, we are able to sample it best. We are seeing the same cell. Once it comes closer, we are not able to sample the upper part of the cell. What does it mean? That means that when you are seeing, suppose, a Max Z product, and you see a cell coming closer to you, you may feel there will be an artificial enhancement in the lowest elevation when it comes around 100 kilometer distance, and there will be a artificial decrease in the height of the cell when it comes closer. So this is something we always have to remember when we are using the radar data for weather forecasting, because oftentimes the radar cells decay when they come closer to when they pass over the radar station. Now, if you're sitting over Delhi, which I am currently, so if you're sitting over Delhi, what is the solution? Do you see the Delhi radar? Not really, because Delhi radar, once it comes closer, the Delhi radar will not be able to give the accurate representation of the cell. It is better to focus on, say, Jaipur radar, which is a little further away, maybe 120 or 150 kilometers, and or the Patiala radar, which will give you the height of the cell accurately. Do you follow that? So always, when you're seeing the radar, when we are seeing the radar data, we are not seeing the data of a single radar in isolation. We have to use the data for any purpose that we use, whether it is modeling, whether it is observation-based forecasting. We have to use the data of multiple radars, either through a network mosaic or through individual radar sampling. If we move further, then what we have discussed is we have two branches in IMD for usage of radar data in nowcasting. First is radar data directly used in nowcasting. This is what an operational forecaster does based on the images available to him or her. The other way of using the radar data is that we assimilate the data into NWP and nowcast models. Madam, how much time do I have, please?
1 hour. So I think up to 4:10 you can.
Okay, madam. Thank you. So when we are talking of radar data usage directly in nowcasting, that is one aspect. The other is radar data assimilated into NWP and nowcast models. This second requirement is what requires the uniform scan strategy, the NetCDF format data, where Kannan was one of the prime people who did this work. So this has been a joint endeavor throughout IMD. Let me be very clear. There are titans in radar meteorology from IMD, Dr. Thampi, Dr. Y.K. Reddy, Mr. Kannan in Chennai. So these are people who have really done a lot of work in making the data smooth and usable, and future radar purchases so smooth that they enter the network without any complication. When we are talking of the first stage, that is radar data used directly in nowcasting, we see that the products that are available to us is, we have animations of the radar. We have the top left is the Max Z product. We have the close to the radar, the reflectivity. We have close to the radar velocity. We have Max Z. We have again PPIV. All these factors are available. And the last is VVP2 product. I'm sorry, I think this slide is a bit too, the figures are too small to see. If you want, I can show you on our, I can show you in our normal web page. On our normal web page, if you see, so this is our radar network operationally available. It is available to the entire country. So here, as you can see, if I zoom in, you have the Max Z product for, suppose, Delhi. This is one of the prime mainly used products. You have close to the radar, the IMDb scan at 150 kilometers. Then you have the IMDb scan at surface rainfall from, I'm showing any one particular radar. Then you have PPIZ at the larger range, for 500 kilometer range, 400 kilometer for Delhi because this is C-band. And then you have the rainfall at close range, and you have the velocity field at the 250 kilometer range. And finally, you have the VVP2, which is a product from all the radars, which gives the vertical profile, estimated vertical profile around the radar. So when we are talking of radar data, this is the data that is available from all the radars. What do we look for in a radar data? Now, here we are talking of what are the things that an operational forecaster looks at in a radar data when he or she gives a forecast. First thing we look for is vertical shear. I will show you examples of what I'm talking of. Second is convergence and divergence. It's a very important fact because we need the convergence and divergence information to detect and to give a prediction where the cells are going to strengthen. Then we see advection, veering, backing of wind. So that gives an idea of advection. Lower level, is there a warm air advection? Is there that will support thunderstorm? Is there a cold air advection in the lower levels and warm air in the upper levels that will inhibit convection? We can see the sea breeze onset. The first, please note, each of them has a huge significance for the forecast we give. Because, for example, sea breeze onset, if we are seeing a late sea breeze onset, you will have your heat wave continuing through the day for that particular day. So models are indicating delayed sea breeze onset, and if at 4:30, 5 o'clock, we are not seeing the first symbols or symptoms of sea breeze onset, we will immediately start to, we will increase our warm night conditions as well as land being hot, we will consider for next day's heat wave. So these are all interrelated with each other. Then we see for velocity couplets. Velocity couplets are small regions of very high positive and negative wind couple, so to say, that indicates that there's a strong rotational component in the region. That kind of regions generally indicate strong thunderstorm cells with rotation inside them. Then we look for discontinuity line in the horizontal. This is a very important thing for us to note, especially we look for maybe frontal characteristics of WD setting in, or we look for discontinuity line in the in the PPIV field to show us where the thunderstorms, new thunderstorm cells will form. So each of these factors determines a forecaster's final forecast. These are all we have discussed are from the velocity field alone. Just by querying the velocity field, by querying the PPIV or the VVP2 product, we get all this information. The ones in blue are by querying the reflectivity field, the information that we get. So in this case, we look for the reflectivity profile in horizontal and vertical. We look at the texture. We look at the height of the cloud. We look for signs of biological clutter. All these symptoms we look for in the reflectivity field. Generally, the first sign of convection starts appearing in the velocity field, and thereafter the intensification or de-intensification starts in the reflectivity field. So when a forecaster works, he or she looks at the velocity field first, the reflectivity field later. These are some brief things because this is something we require very much. I'm not discussing the previous ways of using the radar data for estimating the center of a tropical cyclone. These were the older methods where there used to be the typical cyclone determining center determining curves with which they were detected. They are no longer used. But one thing is, the most important thing is the location of the zero isodop. Zero isodop is where, if you really see, radar reflectivity will be towards the radar or away from the radar. Radar works as a radial wind measurement. So if there is, suppose there is a constant field, say this is a constant field from left to right, okay? This center is a radar. Then the wind at each point here will be the maximum wind speed, which is directly the wind's entire, if you divide up the wind into X and Y components, Y is suppose towards the radar, X is away from the radar, X is perpendicular to the radar. So if the field is a constant field of wind, then you will be getting along the horizontal, along the direction in which the wind is flowing, you will be getting the highest speed, and radar will imagine it to be the highest wind speed. The perpendicular direction in which, if you're seeing suppose a constant wind field, here the radar will detect the wind has no velocity at all, so it will be zero. So this kind of line along the radar, which is the zero line, is called the zero isodop. This is very important for us for locating, without the VVP2, we locate the convergence, divergence, etc. Suppose we locate this kind of a figure, then we will consider that the velocity is, suppose it is increasing, please consider the yellows to be, this is a picture from a book. I'll show you what is it in actual context. So in this case, the lowest reflectivities are in the darkest colors, the lowest velocities are in the darkest colors. The lighter colors indicate higher velocity. So if the velocities have this kind of double C shape, then we know that the velocity is higher in the upper levels, lower in the lower levels. This, I'll show you an example what happens. But this is very significant. Please remember, this indicates that there is a vertical shear in the atmosphere. When we are trying to find out the organization of a thunderstorm system, this kind of a picture gives us immediate indication that there is high shear in the neighborhood of the cell formation. Hence, chances of organization of the thunderstorm is more. Associated damage will be much more. If we have this kind, naturally you have the highest reflectivities in the center as a dumbbell shape. So here again, the velocities will be highest in the middle levels, not in the upper, not in the lower. So this kind of a picture is important. I'm not going into the details, but the two things, one is the backward S shape and the forward S shape. Both of them are indicators. Backward S shape is an indicator of backing of wind, and forward S shape is veering of wind. It is not that throughout the atmosphere this happens. Preferably, if it is in the lower atmosphere, it indicates veering in the lower atmosphere indicates warm, moist air advection. Backing in the upper levels, cold air advection in the upper levels. If both occur simultaneously, then that means first closer to the radar, if we have forward S, and further away from the radar, if we have backward S, oh, that will be the perfect sign for increase in thunderstorm. And this is happening daily on the in the radar data. So this is a picture of Chennai. There was a tropical cyclone Vardha. Just to give you an example, in our case, further away from the radar, you have darker colors, and you can see that two things are there. One is there is that S shape, as you can see. Do you see the S shape? So the S shape is for veering of winds, and also velocity is increasing with height. So high shear, as it is increased, away from the ground, as we go higher, the velocity inside the tropical cyclone is increasing, and there is strong warm air advection towards the radar. So this S shape is a good indicator that there is a lot of the tropical cyclone that has reached here has potential for a lot of rainfall in the vicinity of Chennai. This is for I think this is Delhi radar. Please see in the left top, Delhi radar, veering, we can see throughout the radar, it is a veering of wind. In this case, as you can see, veering indicated that there would be a strong moisture incursion and southerlies coming in. So that really gave a lot of thunderstorm activity over this region where you can see the thunderstorm. The other thing we look for is convergence. Now, convergence cannot be seen in anything else other than the PPI-V product. This kind of arrow shape, we immediately note that there is a chance that at the head of this arrow, there is a chance that there will be very severe convection. So this is something that is available. This signature that is likely to happen is available generally 30 minutes to 1 hour before the actual start of the convection in the reflectivity period. So generally the convergence starts first, then the cloud starts to build up, and then the main damage happens. So there is another picture. In this case, this is for Kerala, Kochi. It was on 21st of August this year. I want to show you a particular video actually. That is what I was trying to put in, but it is not. Sorry. Oh, sorry. Yes. Sorry. Do you see this is this moving, please? Is there a video moving on your screen?
Yeah. Yes.
Oh God. So, okay. So I will decrease the speed. So what is it that you are understanding from this? What is it that you understand from this? First of all, please note that there were very high winds away from the radar. I mean, there was a high vertical shear. I will stop it. Okay. Okay. Now, here, if you see, this is a typical case of winds gradually strengthening with height. So this is over your Cochin station, and you can see that there is high. I mean, just not at the ground, but much above the ground. I mean, gradually the winds were strengthening with height. Now you see what happens gradually. Please note what has happened. Those high wind speeds, or rather the what we were seeing as wind speeds higher at upper levels, have once they've come closer to the coast, they have gradually come closer to the ground. So please note what is the wind speed in this particular case. You can see that it is, sorry, this is unreadable, plus 14 to minus 14. So 28 meters per second, which comes to 54 knots, which comes to 100 kmph. Not 100, 14 to the 28 to the 56, sorry, 56 kmph winds were coming towards the land. So this is a signature that you must have seen this on this particular day. Anybody who's from Kerala can verify that there were severe thunderstorms in the neighborhood of Kochi. Once this kind of a high wind speed region gradually came in the lower levels. So this is, if you see the corresponding reflectivity, reflectivity does not really show such tall clouds, but you still get reflectivity field does not show very tall clouds. Did I make a mistake? Yeah. So, but the height of the cloud. So this is again a thing that one has to be wary about. The data, a lazy forecaster generally makes a wrong forecast. If we just go by reflectivity data, it has no indication that such strong wind convergence was taking place over Kochi. But if you see the velocity field simultaneously, we get an indication, and that happened 2 to 3 hours. No, not 2 to 3, 1 to 2 hours before the actual event. So nowcast can be accordingly increased when we are giving a forecast. The other thing is we are talking of sea breeze onset. Please note that this is a scale that is in UTC. So that I hope is in UTC, but anyway, the point is, yeah, that is in UTC. Now, if you see very clearly, what I was talking about, the onset of sea breeze. Are you able to follow? I hope you're able to follow. Okay, Mr. Tete Han, you raised a hand. Do you have a question, please? You can type it in the message box. Otherwise, you can ask.
Ma'am, we will be taking the questions at the end. So
Excellent. So here, this is what I was telling you about the onset of sea breeze. It is theoretically true that the sea breeze onset happens in the evening, but depending upon weather systems, depending upon their location in respect of the coast, sea breeze onset can happen earlier or later. This can determine very much the whether, suppose in this particular case, the sea breeze onset started from 6 UTC. 6 UTC means at 11:30. Sea breeze means it's cold air, cool air, moisture-laden air that is coming in. Two things it is indicating. It indicates that temperatures are likely to fall along the coast. That is very, very big information. It is like that temperature fall is likely to be not just at the coast, but somewhat inland also. So if we are giving coastal heat wave, we will immediately decrease the heat wave warning. That is a very important requirement for us. So on a nowcast scale, we also decrease our heat wave warning based on the onset of the sea breeze. Please remember, to the right we have the sea breeze. This is sorry. To the right we have the sorry. This is over the radar. So Chennai initially northerlies becoming easterlies. So Chennai winds are turned easterlies, means winds are coming in from the sea, and gradually the depth of the easterlies increased by the late evening by 12 UTC, which is around 5:30 p.m. in local time. The sea breeze depth was around 1.2 kilometers. So this is a very big thing. That means from starting from just the surface up to 1 kilometer, the winds have gradually built up. In this kind of a scenario, we'll have two things. One is heat wave will reduce over Chennai. And yes, please.
Can you put the full screen?
Yes, sorry. Please
Okay.
repeat if I make the mistake. Yeah.
Oh, okay, thank you.
So two things. One is that sea breeze onset has started early, means today the heat wave effect will be reduced over Chennai and the neighborhood or all along the coast, because it is not a very localized phenomenon. Second thing is, when such deep and strong easterlies come in, if the winds on the west, that means the land winds are dry, this is also high probable region for thunderstorm occurrence. So late evening thunderstorms are very likely in this kind of a scenario where the winds are depth of easterlies, strength of easterlies are increasing. Now we come to the reflectivity data. The reflectivity data is something that is coming to us maybe at the last stage of our forecasting. I will show you what is our forecasting strategy. This is the scenario when thunderstorms are already happening, but you have to give a prediction. So in the reflectivity data, what we look for is the bright band, the stratiform cloud region, the convective cloud region, and their movement. So when a person has to give a warning, like it happens in our context that clouds are seen in Patiala, or let us say it is seen in Patiala over Firozpur. Now we have to give a warning. Whether do we give a warning for further to the east, Hisar? Do we give a warning for Hisar, which is further to the southeast? We will not only be seeing the velocity field, we will also see the reflectivity field. Now here, the speed of movement of the thunderstorms, the way it is moving, and its other factors that are coming in, I'll discuss the other factors. All those things determine not just whether there will be thunderstorms, but what kind of thunderstorms will happen in, say, Patiala. Whether there will be, now suppose, for example, in this kind of a structure, whether to the left or to the right, the region of convection, which is the easternmost region, is generally the region where you get the lightning, the thunder, the hail, or the squally winds. The region to the left, which is that flat textured, smooth textured region, is generally where you get a bright band and you start seeing persistent rain with not much thunder. You might get some annual thunder, but not much thunder, and no downbursts or squalls or hail. This is a very significant information in the hand of the forecaster, because he or she need not give the same forecast for the entire region. They can give a different forecast for this region when it is moving, say 1 hour later, if they have to give a forecast for, so this is Delhi radar. Okay, for Delhi radar, if it is to reach Bareilly, and they're seeing that this other factors are favorable, they will give a different forecast for Bareilly for 2 hours, and a different forecast for, suppose, what is this region? Whatever, to the left, you'll gradually be decreasing the forecast, nowcast, this thing. This is in the nowcast scale. You will be giving a different nowcast for this entire region, because these cells will gradually move eastwards, giving this kind of thunder and lightning and other weather. And behind it, you will only give forecast for nowcast for light rain. You will not give more higher level of alert, warning, impact-based warning. We will not give high. So this is one tool in the hands of forecasters. Other than this, we also have our season-based, suppose for Delhi radar usage, we have season-based when our Delhi radar is issuing a nowcast, at what reflectivity they'll start to give issue the rain. Like here you're seeing at 20 dBz, at up to 20 dBz is plotted. But if it is a monsoon season, light rain will start at 15 dBz itself. So these are things that are very local in terms of impact, and the radar person has generally uses a different calibration for different intensity for monsoon season, for winter season, and for the pre-monsoon season. Okay, so having said this, these are from our operational manual, that this is how the Delhi radar gives a warning. So similar things are there for each radar. Precipitation measurement is again a very complex fact from radars, because mainly a lot of errors are possible from the radar data measurement. So from dual pole radars, it is easier, but from single pole radars also, the rainfall can be measured, but maybe not accurately, but it can give a systematic value where the highest rainfall is coming. For example, we do not have a station and in a particular location, and we wish to extrapolate to what has been the rainfall over a particular region. Then the radar rainfall map, SRI rainfall map, gives an indication that which is the region which received the maximum rainfall according to the radar. So that is a good indication for using radar data. If you don't mind, it is already 4 o'clock. I will not go into model-based forecasting today, but I will leave you with this particular slide, which I will come back to again. We have been discussing radars so far, but please note, radars are not the only tool with us when we are doing nowcasting, for the simple reason that in an operational setup, unlike when we are doing a case study, the radar data is not always available for us. Sometimes the radar is down, sometimes some areas radar data is not available. So everything has to come together to give a forecast, a nowcast. More than the forecast, the nowcast. I will take you back again to that first or second slide I showed you. You have to give, in order to give a nowcast, you have to depend initially maximum on the observation products, to a lesser extent on model products. So when we are giving a prediction, we will be depending from the medium range, which are colored in yellow, in orange, down to this scale in green, which is the nowcast scale. As you can see, in the nowcast scale, for longer ranges, we will be looking at the nowcast models. Closer by, we will look at satellite data and products. Still closer, we will look at lightning data and products. And only in the final stage, we will look at radar data and products. Along with that, impact information is attached, and then finally a nowcast is generated. So please remember that an operational forecaster's tools are not one, but multiple in order to give a reliable operational forecast. So only then can they give such a diverse set of forecasts for any particular district or station. And these are verified, and verification goes on, and the verification skill is judged as to where and why we have a forecast decrease. I will just say this much about our forecast accuracy. Generally, our forecasts are more accurate. We get 85 to 90% accuracy, where, or in months or regions where thunderstorm, which are more thunderstorm prone. Why I'm saying is, generally, suppose March to June, the forecast accuracy improves. West India forecast is generally poorer than East India. And in some months where thunderstorms happen a lot, suppose over Central India's forecast accuracy improves. This is a general thumb rule that we have observed. And this is not just for thunderstorms, for most systems. That is because forecasters' accuracy also improves. I mean, confidence also increases when there is organized weather system that is giving a lot of thunderstorm activity. Isolated thunderstorms, generally, the first slide that I showed you, cumulus to cumulonimbus, will it happen? That remains a question. Thank you. If you want, I can take questions regarding this.
Thank you very much, ma'am. I think we have only 2-3 questions. Then question answer session will be moderated by Dr. Ragesh.
Okay.
Therefore, there's 2-3 questions. First question is there a reference book to read or recognize the patterns of radar image? For example, S pattern, arrow, and so on.
Yes, there is a very good book. There is a very good paper. These are not mine. I have not given the reference in that, but if you want, I can share the reference after this. It's a very good, you should read that paper. Anytime you are looking at the radar data, you should use that particular paper to refer back to. It is a standard for all operational meteorologists. Any other question?
And next question, how we are recording lightning data?
How we are recording lightning data. This is not part of radars, but we'll tell you nevertheless. Lightning data can be from ground-based sensor network. It can be from the satellite-based sensor network. The two methods are different. Satellites measure the electrical scintillation on the as they're viewing the ground. So electrical scintillation is that electric field perturbation, so to say. So satellites have longer period data set available because of for many years, especially polar orbiting satellites have been used for measuring lightning. But in more recent years, suppose GOES, Meteosat, and in the future, our INSAT satellites are also going to come up with a geostationary satellites are going to come up with a payload which will be able to measure lightning. Ground-based lightning generally is more accurate in terms of location accuracy compared to space-based lightning measurement. Here also there are multiple methods. The most commonly used one that we have in India is the Earth networks. I think multiple states have it, and IITM network has it. Indian Air Force, they have also a network. They measure on the base of triangulation. So something like a GPS, any scintillation in the atmosphere, they will measure in terms of that is picked up by at least 3 or 4 sensors. So they will give an idea about X, Y, Z, and T for the particular location of the scintillation, location of that flash. Now, depending upon the wavelength band it operates in, there is the Vaisala network, there is the Earth networks, there is the Boltec network. So they all operate at different frequencies, and correspondingly there is difference in the lightning measurement from each of these networks.
Okay, madam. Next question. Can you elaborate on the event that occurred in Wayanad?
Which event is he talking about?
That,
This,
that Wayanad landslide event. That may be the question.
no, I don't have that material with me. We had our Kochi radar, but I think Wayanad is in the hills. So radar's efficacy I have to check up. I have not particularly checked the Wayanad episode. I have to check up and then I can get back.
Okay, ma'am. Next is a long question. In case of non-availability of radars for an area of interest, only lightning network data is available. How
Sorry.
can you, in case of non-availability of radars for an area of interest, only lightning network data is available.
Sorry, I'm also handling the media and there was somebody's call. Please carry.
Okay, okay, I will start one more. In case of non-availability of radars for an area of interest, only lightning network data is available. How can you classify an area with lightning spots with regard to light, moderate, and severe thunderstorm?
Exactly. This is the real question that we have to address. Please note that, especially for example, Jharkhand, North Chhattisgarh, these are radar holes. These are radar holes where you do not really get radar data availability, and so you have to depend a lot on lightning. Can I go back to that last slide, please? Where is exactly? This is a very important slide. Can I share it?
This one I can share.
I can answer that question.
Please share. Yeah. Why not?
Is it? Yeah. Okay. Yeah. So the question is basically, if you remove this last point, then what happens, right? If you just remove this thing, which is very true, which is very possible. But please remember that this is where an SOP comes into the picture. What we really have is, we look at multiple things. First of all, we look at whether that has already occurred. How do we look at whether that has already occurred? We look at our AWS data. We look at the SYNOP. We look at, so all this data is available real time with us. If it is, then we look at all the other information from the Nowcast models, which are showing that, okay, their movement is somewhat likely to a certain direction. We look at satellite data and products. Now, satellite data is not just reflective, not just the cloud CTVT we look at. We look at the vorticity, divergence, convergence, shear. All these 4 products we look at all levels to see whether there is an increase or decrease over a particular area happening. So if you have had thunderstorms, we also look at the metadata, which is also available to us online. If you are looking at any of these are saying that a system is moving in the westerlies, it has already given hail over a certain region, same system is coming to your location. You can check it from the lightning data, which is coming at 5-minute intervals, to tell you that, okay, that region of lightning increase is gradually happening, coming towards you. We automatically increase our level of warning. We give similar warnings to what was there in the which has happened in that weather system a little further back, maybe 1 hour back. If that system is still persisting with a similar intensity, it is likely to give similar weather over our region. So here we are doing something of a persistence or extrapolation based forecast, but a manual way. Do you follow? Because all India, we have to give a nowcast and we have to give as much accuracy as possible. This is the way, suppose in Jharkhand, when a forecast is issued, this is the main fact that they take into account, the way the lightning is changing, whether it is increasing, amount of lightning is increasing, direction in which the lightning intensity flashes are increasing. These 2 factors, along with whatever has happened in the past, along with what is the model forecast, along with what is the satellite prediction of increase or decrease in vorticity, convergence, divergence, half-hourly data is available. We take all these things into account before the forecast is issued. Is it okay?
Okay, ma'am. Next question. How do you foreshadow a gust front event?
Okay, for example, for a gust front, we are not, can I minimize it? Stop sharing. Okay. For a gust front event, like I showed you for this Kerala episode, when we are seeing high shear in the atmosphere, and we are also seeing that the winds are gradually, those high, strong winds in the upper levels, because here the low level jet is there. So we are seeing the jet descending to the lower levels. Immediately, we have an indication that there will be a strong wind event happening over this region. There is another thing that we also look at. We also look at velocity couplets. That in fact, in that Kerala episode, again, can I share my screen, please?
Yes.
Suppose I share my screen. Yeah. So Kerala. Yeah. Yes. So can you see this particular screen? I was talking of velocity couplets. Okay. This was a little earlier in this thing, but please note that, do you note the thing here? Whatever is, can I make a point? Pointer options, pen. Do you see this small region here and here? So what does it mean? You see what exactly is the thing? It is -2 and this is, sorry, this is +2 and -6. Something like this kind of a couplet has formed. Do you see these two? Not this. Not this. This is the zero isodot. But do you see these two couplets? Here, whatever cells that are forming will be generally more intense than other cells which are forming. One thing is that you can see here clearly that the wings are strengthening towards the ground, like I showed you in the animation, with time. Along with that, these cells, if they're also coming towards the inland, and this frequently happens, especially over Bihar, this kind of couplets. So immediately we know that there is a strong rotational component in them, because this indicates that there is a very strong pulling and pushing happening here. This is not part of the zero isotope. Zero isotope is somewhere here. Zero isotope is somewhere here. So no, sorry. It is somewhere here. Here. Okay. But here there is a different thing that is happening. These are velocity couplers. So this is second signal. Third signal we look for is this kind of a convergence zone. If we see convergence zone, so this is from Nagpur radar, and this is from which radar? I think some other Delhi radar maybe. So once we get it, then we immediately know that there is a very strong convergence. Thunderstorm. See, thunderstorms will be the same. If the intensity is more, then you'll have either hail or squall, depending upon other things. Like you'll see the reflectivity value is more than 50 dBz, you will start giving a hail. Like I have mentioned here, if we are seeing a reflectivity more than 50 dBz, hailstorm. If 40 dBz, we'll give dust storm, light to moderate intensity rain. So these are the thumb rules we use along with that other information to give a warning for gust front. Yes. Any other question?
There is no other questions in the Zoom. I will check the YouTube. No, madam. There is no other questions.
Okay. Thank you then.
Thank you very much, ma'am. Actually, we have to have a photo session now. So please, everyone switch on the camera.
Okay. So I need to have this camera here. Okay. Is that okay?
Okay, ma'am.
Maybe not. Okay, fine. Thank you, madam. Thank you, sirs.
Thank you, ma'am. Now I invite Dr. Paulami Chakravarti to extend vote of thanks.
Thank you, ma'am. I'll share my screen if that's all right. I think
Yeah,
the
you can share. Yeah, you can share.
yeah, I'm trying to. It is. I think I'm not allowed to share right now. Can I just read if it's okay?
Yeah, you
It's,
can read also. It's fine.
yes, I'll do that. I'm sorry for the issues. So esteemed.
You can share.
Oh, okay, okay. I'll do that. Wait. Let me show. Yeah. It's, esteemed guests, distinguished speaker, and respected colleagues, as we conclude the 13th lecture of the Radar Meteorology lecture series, it is my honor to extend the vote of thanks on behalf of the South Asian Meteorological Association, the Advanced Center for Atmospheric Radar Research, and the Cochin University of Science and Technology, India. Firstly, I express our gratitude to Professor Someshwar Das, sir, Secretary of Sama, for his vibrant welcome address that set the precedent for the lecture. We also extend our heartfelt gratitude to Air Vice Marshal Professor Dr. Ajit Tyagi, sir, President of Sama, for your educational opening remarks and unwavering dedication to guiding the youth of our generation with your tireless efforts. We would like to express our sincere commendation and gratitude to our eminent speaker, Dr. Soma Roy, ma'am, Scientist F, IMD India, for your enlightening lecture on DWR utilization in nowcasting. We deeply appreciate Dr. Swagata Paira, sir, Treasurer Sama, and Associate Professor at the BIT Mesra, Ranchi, for the eloquent introduction conveyed by him for our guest speaker today. We also deeply appreciate Mr. Rakesh V, instrumentation engineer at the CUSAT India, for his efforts on moderating the question and answer session and making it a lively and productive discussion. Lastly, a big shout out and our heartfelt gratitude to Dr. Shrikala, PP, Assistant Professor at the CUSAT, for overseeing the entire session and seamlessly orchestrating the radar meteorology lecture series. Also, I would like to thank all the participants that were present for their active engagement and contributions. And once again, thank you, all of you who were present today and those working on the sidelines for making this session a success. Thank you. I'll stop sharing now.
Thank you, ma'am. Now, I think Someshwar Das can give some concluding remarks.
Well, okay. Thanks, Dr. Srikala. I would like to thank Dr. Soma Roy for the interesting lecture on nowcasting based upon the weather radar. I would not like to take much time because I know how busy she is, because at 4 o'clock she was supposed to be with the DG for the briefing, and you could see that while presenting the seminar, she was also getting the questions from the media on her telephone. So we can imagine how busy she could be, especially now when there is a cyclone in the Gujarat coast. But people in the weather forecasting center are always busy like that. And by the way, next week on 7th of September also she is traveling. She will be in Pune, and she requested that whether it is possible to change that. But then I requested that even if she is in Pune, she can still deliver the talk because it is an online talk. And so she kindly agreed, although she said that there are some problems in the campus. I am the campus in Pasan about the network issues, but she will try her best to deliver the lecture also on 7th. So thank you so much, ma'am, for your lecture. And I know that how much efforts you have made all over India in making this Doppler radar products available for the nowcasting, the weather. Everywhere you have traveled and also trained the people on nowcasting. So obviously There has been a lot of interest in your talk because I can see still a lot of people are present. They have not left the session, and the kind of questions they have raised are also quite interesting. Somebody was asking about the Wayanad, whether lightning in the Wayanad could be detected or not, various kinds of. But I would like to tell the participants who asked this question: have you ever tried to look at the radars which are nearby Wayanad in Kerala? Without looking at that, you should not ask the question. You should know that there are two radars in Kerala. One is at Kochi, which is about 250 kilometers from Wayanad, and another one is at Trivandrum, which is about 400 kilometers from Wayanad, right? Although these radars are S-band radars, going to be cyclone warning radars, and can have a PPI range of almost like 400, 500 kilometers. But yet, if you are so curious, you should go back and see Wayanad is really covered by the radar or not. Many more radars, and in course of time, of course, you have an umbrella of radar, maybe almost like more than 90 or 100 radars will be there all over the country. But till then, you should understand the gaps, data gaps. Also, somebody was asking about the lightning in the absence of radar. How can we estimate the severity of the thunderstorms? Well, there are many ways to do that. First of all, lightning itself, we should have the access of the lightning data. And also, I don't know whether you are aware of the lightning forecast, which is provided by IMD, IITM, and NCMRW on a very regular basis, right? On a real-time basis. And they provide the lightning potential index, lightning flash rates, all that. Okay. So in case if the radar is down, not available, then you can always look at those products and to understand how severe is the thunderstorm, depending upon the. They also give a categorized products like a moderate, very severe, or light lightning potential index, etc. So if you are really interested and serious to learn this thing, you should look at all those products and come prepared to learn more in these lecture series given by the experts like Dr. Soma. So thank you once again, madam, for delivering very nice lecture, and hope to see you next week on Saturday, on 7th. Thank you.
Hopefully, I'll be able to do it, sir, without any network issues. Thank you, sir. Thank you, everybody.
Thank you. Thank you, sir.
Thank you, sir. Last word by Tyagi sir. Is there? Oh, but the speaker has gone. The speaker has logged out. So because she has another meeting. Okay, all right. So can I end the session?
Yeah, we can end the session, sir.
Sir, we will end the session.